Thanks a lot, Paul. You may have this little hiding bar that comes up and down. What I'd like to do today is talk about some of the research I've been doing locally, as well as regionally, as well as worldwide. And the last site we'll take a look at is one of many sites that we're working on in Eastern Europe, and it's tying the idea of, as geoscientists, aiding survivors in their communities and these marginalized people, and trying to find where the mass burial sites are. And so we'll talk about that a little bit at the end. I'd like to, as an outline, do some brief background of how I got into this, talk about methodology, this being a tool that's been used. It's used much more in Europe and Asia than it is in North America. Focus in on some coastal, local, as well as regional, aeolian, and then finish off with Holocaust mapping. And Daryl Smith is the one who dragged me down to Bonneville and to take a look at Lake Bonneville. He loved this area. We came down here numerous times, including swaying me to come down for every 2 days in the field, 1 day of skiing. And we did that for multiple years, collecting data sets. So we'll take a look at it. The funding for all these projects comes from a variety of different organizations, including the ones noted here. But I started back from Simon Fraser University doing seismic work, shallow seismic work, to take a look at the top of the Fraser River Delta. And we were interested in that work to understand this post-glacial environment as this delta was prograding out in the Juan de Fuca Strait. And it had huge implications on earthquakes because we're anticipating, just like a lot of places along the Pacific Northway, a magnitude 8 or 9 earthquake. And we've mapped the ones in the past. And so we're anticipating one there. And then you build a whole you build a whole community on top of this deltaic sediments. What's going to happen? And so part of our work was that. As we were working with that, this is a lot deeper seismic, taking a look at these cliniform reflections working in the oil and gas industry, taking a look at reservoir characterization. And so I've been here many times to Utah to work with Exxon, to go out to the Panther Tongue, to go out to a lot of areas. And we even have a ridge at Exxon called Radar Ridge, where we collected the data to take a look at what's in the subsurface. But we can take a look in these areas and see these cliniforms at a lot larger scale. And we can see the depth here is 70 instead of kilometers into the subsurface. But what's of interest that happened when we could start building, laptops and building these things, right, is now we could have the electronics to sample at such a high rate that we can now record waves at the megahertz range. And so this is a ground penetrating radar profile that I saw at my first ground penetrating radar conference. And the question is, what do you see, right? And this is part of when I run some workshops, we go through these and take a look at interpretation. We see some horizontal to subhorizontal layers. We see an erosional truncation that came into this feature, right? We can see some subhorizontal reflections again. Then we can see some dipping reflections, these cliniforms, and then we can pick up some reflections that are dipping at slightly shallower angles. And so we could go in a lot more detail and describe this, but hopefully one thing you realize is that I never told you what environment this is. Some people would say this is fluvial. Some people would say this is aeolian. Some people would say this is glacial fluvial. And you could go on. I don't know what environment this is, but we can still interpret it. It is not this, right? But this is what people expect us to do in this field. They want to know where to dig, where to find the fossils, where to find these things. And that was the big blooper right at Jurassic Park, right at the front end. They were using the wrong geophysical method and then describing another one when they were looking at the screen. So what is ground penetrating radar? We're emitting an electromagnetic pulse into the subsurface. We're recording those echoes, very similar to shallow seismic, and we're building an image of the subsurface stratigraphy from those echoes or those reflections that are coming up from the subsurface. Be it, right, geological horizons, or B, those archaeological horizons. We're working in basically the 1 to the 1,000 megahertz range, so the same range that you listen to radio on. And from that range of frequencies, the lower the frequencies, as we'll talk about, the deeper we can see. The shallower or the higher the frequency, the more higher resolution we can pick up. And so much of the engineering, you could say, geology that goes on, looking at structures of bridges and how we're going to build those areas, as well as in Europe, they got huge labs that are using radar to figure out the integrity of a bridge. Interstate 35 that went through Minneapolis collapsed multiple years ago, went right into the valley with many people killed. And it was a structural deficit on that bridge that caused that. You're looking at this screen from 0.4 to 0.7 megahertz, right? And they're not megahertz and microns. And that's the only frequency you can see. And so we have to remember, as geoscientists, there are many other frequencies we can use to take a look at the subsurface. They tell us different properties. And so looking into the subsurface, we need to take a look at what we're looking for and how to set things up. And this is an older photo setting up in a coastal environment in the West Coast. We have the transmitter antennae that's sending those signals into the ground. The receiver gets those signals back up, and then we take that through fiber optic cables, and then we can take a look at those on the screen. And so we can collect data and interpret it almost real time as we collect it. And so we are basically doing an optimum offset shallow seismic. We are shooting our transmitter. The waves go down, reflects off reflector and subsurface, comes up to a receiver, and we step that along, and we continual step that along. At higher frequency antennae, you'll see in archaeological sites, you will see it if you're working for, let's say, a utility finding company. Those are the largest users of ground penetrating radar. In Wisconsin, we had where they didn't do the utility finding correctly. They dug, they hit a gas main, blew up, and multiple people were killed. And that's huge legislation going on in the United States, taking a look at that. And radar is the tool they're using for that. It's such a big tool. The company that equipment I buy from were bought out by the largest utility finding company in this country. So we can work at a very different environments. Rough environments is a clear cut here. We got transmitting antennae, receiving antennae, and we're moving those along. And this antennae is for a higher frequency in, and the first wave we're going to get from the transmitter to the receiver is that air wave. The second one is the ground wave. And so all the profiles you see today will have an air wave and ground wave up at top. If you deal with shallow seismic or seismic, though, these are noise into your data. So we could get rid of them right off the bat. And then your reflection off the targets in the subsurface are coming in afterwards, time-wise. So you have the arrival of the air wave, arrival of the direct wave, and then the arrival of your reflected waves. And those can be multiple that we see in the subsurface. And this is a time-based technique, right? You're sending a signal going down and it comes back up and you're recording time. To get depth, we are going to have to, get rid of this again. You're going to have to calculate velocity. And so the three big properties that we deal with is velocity, dielectric permittivity, or the contrast between different sediments. Because people say, well, I don't see that horizon between, let's say, sand and sandstone. Well, they may be the exact same dielectric permittivity, and therefore you're not going to see the difference. And that's why at archaeological sites, we often don't see things, because everything is the same dielectric permittivity. There's very little change. And then attenuation or the absorption of the signal. So velocity, we can calculate doing what we call a common midpoint measurement, same as shallow seismic. We step the antennae out from that center, and from there we have a distance time plot, and we can calculate an estimated velocity for that. Remember that air wave is the speed of light, so it's always going to be 0.3 meters per nanosecond, regardless where you go in the world. Everything is going to be slower than the speed of light. The second thing is dealing with conductivity. This is a log plot. And what we can see is as conductivity increases, your depth range decreases exponentially. And so this can be a huge problem. We were talking earlier about working on salt. And salt will be great to work on as long as it's dry. It's very resistive. As soon as you add a drop of water on salt, it's conductive. And now you can't look through. So GPR is a great tool in salt mines, but if you get any water in there, it's not going to see anything. So it's a range of frequencies depending on the companies you look at is roughly the same. There are some FCC regulations going on that Mike talked about earlier, but this is essentially your range of antennae that you can have. High frequency, dealing with really high resolution work, low resolution, the lower frequencies for that low resolution, but you can look a lot deeper. And so what you can see here, 1 meter, very shallow to 50 plus meters with that higher, so with that longer antennae, but lower frequency, but your resolution decreases. So if you're interested in where's the bottom of the glacier, you're going very, very low megahertz. You're not going to see a lot of detail resolution, but you'll pick up those boundaries versus the other way around. And so here's an example of the trade-offs that you get. Here on the first one at 250 megahertz, we can see deeper. We can see some more features, but they're not high resolution. And you get higher and higher resolution as you're moving to the right. And so if you had to pick up a pipe and you had to tell the contractor where there was no dig in that dig site, right? 500 megahertz is that sweet spot that they would use. Most of the utility companies have that piece of equipment, that antennae on their truck. I use, people talk about geometrical correction. I use a laser leveler. GPS is a great tool until there's trees above you, and then it doesn't work. Or you're working inside a cave, right? And things like that. And so I've used a laser leveler as a quick tool to be able to get that topography. If you're out in the desert here, right, you got great access to satellites and things like that. But as just the way I collect that topography, and then we record that into the notes, and then we can correct that using Excel and correct those topography. And then we can get features like this where we can correct these signals as they come back up, and we can get that groundwater table to be roughly flat as it comes through. Otherwise, the groundwater table is going to move up and down. So what's so tough about GPR? And I think we realize as geoscientists, right? The subsurface is complicated. It is not straight up, I teach a lot of intro classes, right? Yeah, it's easy at that level, but once you start understanding the details, it gets a lot more. So let's take a look at some sites. This is on the Baltic coast, and this is the Fordune that is along that Baltic coast in Lithuania. And you'll see these horizontal to subhorizontal, nice coastal deposits that are building out, and then all of a sudden it dies. And so in this case, we're encountering that marine water, that salt water that's in those areas. And now we could completely conductive sediments, and we can't see any deeper. So this situation becomes problematic. When we work out in Lake Lahontan, on the Russell Spit, we've been there multiple times in different sites. And I don't know why, right? There's a lot more silt or clay in that system, or there's more saline environments. It's much more conductive when we don't see as deep in those environments. And I've worked with a couple different people, and I'd love to go back. I love the area, right? But we don't necessarily see as deep. William River Delta here, and this is in northern Canada. A stunning deltaic environment, and we get beautiful cliniforms reflections that come up in this environment. And I've been told multiple times, once your sediment is wet, it's conductive, and that's not true. Water itself is quite resistive. Slow velocity, but it's resistive. And therefore you can see that the groundwater table is right at the top here. And we can see beautiful stratigraphy through these areas that we've collected. This is Lonesome Point Barrier on Lake Superior. We're just going to show an example here. This is probably one of the largest barrier systems, I think, in the world when it was developed in the Holocene. It's now eroding away. But the reason I say that is we take a look at these reflections here, and we're down 45, 50 meters here into the subsurface where we have a barrier system, glacial fluvial outwash. This is sandstone here, we think. The neutrinos are saying otherwise. They think this is all sediment, not sandstone. So we've got to work through that. But just to show you is how deep we can see with that radar in, plastic sediments in these areas, and then also through bedrock. So this is out in Australia, taking a look at another coastal deposit. And as we go through here, we're collecting on the beach while everyone's swimming, right? And we're seeing some nice coastal deposits. You see erosional beach faces coming up here and then building out. But at 200 megahertz, which is a higher frequency, we have such large amount of reflections going on here. The question comes down to, can we see the forest? Because there's so many trees here that we can't see the bigger picture. And this is that sweet spot of trying to figure out what frequency works best for you, for your project. And for most plastic environments that I'll be showing you is 100 megahertz, because it's that sweet spot that you can get the overall picture. There is no textbooks out there that can show you this much detailed stratigraphy, right? We just haven't been done yet. And so that's where some of the details in the future, right? Future students, this is all kinds of detail. So let's look at some, now we showed how GPR works, the different environments that it can work in. Let's take a look at some coastal areas. We've shot a lot of places around the Great Lakes. Just want to show you a couple that I used pre and post my original times coming to Bonneville. And you'll see why in a sec. This is Rondo Provincial Park in Ontario in Lake Erie. You can see the barrier system that's coming up in the upper right there. And these are dipping reflections, usually about 4 to 5 degrees dipping, that are prograding out towards the lake itself, always prograding built out. So this is what we would call a progradational coastal environment. And we can see this in this environment. There's a couple more as we've done in this area. This is Park Point in Duluth, Minnesota. We've been doing a variety of different work with students. And again, this is going across the barrier system from west to east. Again, 4 to 5 degree dipping planiforms going all the way across the barrier system. Okay. And so this, I see this over and over and over again on coastal systems around the world. I very rarely have found overwash deposits, right? Are they in our stratigraphic record? Are they in the book cliffs? Are they in these areas? Because we like to interpret overwash, but we don't see them. Geomorphically, they are, air photos, they're there, but when we go do the stratigraphic work. So we went to Willapa Barrier Spit because this is an analog to the Panther Tongue, to places in the Book Cliffs with high tides that are coming in and out of these systems and high waves that come into these systems, very active areas. And so this area has got a 160 kilometer long littoral cell. It is tectonically active as we go in these areas. And the Willapa Barrier Spit itself is just about 40 kilometers long. It's about 3-4 kilometers wide, depending on where you are. The high tide range, high wave energy, and fine to medium grain sand in these areas. And so the question was, when we were here with oil and gas reservoir characterization workshop going out of Calgary, of if we're on this coastal system, which way should be depositional dip of the barrier system? If we shot a GPR grid here, or we grid here, should the dip be in this direction or should the dip be in this direction? Realizing, okay, longshore drift is in this direction. which way should the depositional dip go on? And so we went out early morning, got up early and collected, and this is the data set that we collected. And this is going towards the Pacific Ocean. It is an opposite to the direction of the longshore drift, right? Which in many textbooks, that's the way it is. And so the oil and gas industry, you collected that wrong. It can't be, because we directionally drill based off longshore drift of where we think that is going in these areas. And so we've collected lots of data in this area since, because we can see the beach face that happens. We can pick up the water tables as they go through and go through the foredunes. And then we can also pick up the soils. And so we can see these multiple horizons within the foredunes as these soils have built over time. So if we can do that, we should be able to pick up this progradational sequence in these shorelines. And so what we did is we got aerial photos that went back in time, as well as the Corps' original logs in 1886 to see where the shoreline was. And we can see how much it's prograded out. And then we did some coring and dug some pits, and we can see there's these heavy mineral layers. These are magnetite and ilmenite that are coming out of the Columbia River, and then get deposited along the shoreline. And I think we have to remember it's electromagnetic. This magnetic portion of the electromagnetic wave is what we're picking up here. And so here are these reflections we're seeing, the constant reflections. And our interpretation is that every reflection is a year. We're seeing a reflection every year. It builds up. Winter storms come in, you erode back, but you never erode back far enough to erode the previous year. And you continue to build up that area. So from that, we can build an aggradation or progradational chart. And if we know that, we can tie it to climate. So now we have a climate signature of El Niños and La Niñas in this area based on how far and the timings of those, because we know the climate record, we know where the reflections are in space, and now we can tie that into these areas. And you'll notice that some of these areas will be thinner. You've got a lot more storm activity, and then wider if there's less storm activity. So at that study area, and this is where we originally started, there's that study area. We did a whole bunch of tests, but I'll just show this one, is that we can collect the 3D grid, and then we can throw a 3D grid into 3D visualization. And there's all kinds of software out there. Oil and gas software probably by far have got the best. This comes off with size. And so what we can do is we can cut through down those time slices. And what we can see is that shoreline is not directly perpendicular to the ocean. There is that northwestward dip of the beach, each individual beach as we go through that. We can digitize those. And now we can produce an individual beach face from 30 or 50 or 100 or 1,000 or older, and take a look at what that beach face looked like. We can do that to whatever layer we want in there, and we can calculate that. Now we have that, we can now subtract, and we now can calculate a volume of sediment that has moved through the system between those 2 years or 3 years, and calculate that. So now we have basically a sediment budget that's moving through this system. And we wanted to prove that we could do that with this area. In addition, as we were collecting our data, right, when we processed the data, we came across these dipping features, and some were steeper. And as those ones became steeper here, we reprocessed that and said something unusual is going on. And we processed it in different ways. Here's another way of looking at it. You can see there's a huge erosional truncation that comes up here. And we said, we got to shoot a 3D grid, and we got to pour on this site. And this is a 3D grid. You can actually pick up that surface. And this is basically a magnitude 8-9 earthquake in the Pacific Northwest. The whole land, when an earthquake had, the whole land drops about a meter and a half. And then it slowly rebounds up. We don't know how fast. That'd be a really neat study to figure that out, because I think it's in here. How quickly that'll rebound up, and then it'll start prograding out again. And then you'll have another earthquake. And we picked up 7 of these earthquakes. So with 7 earthquakes in the last 3,500 years, if you do all the calculations, we are now due for another earthquake in the Pacific Northwest. If, right, you take a look at the recurrence interval. So that was pretty good. We've done this in all of them. We've dated all of them. And so we know exactly where they are on these systems. And so why is that of interest? The Panther Tongue here, right, which we could drive to, right, take a look at. We shot GPR on there. It's the exact same thing as what I just showed you there. This is the why we did a lot of that work as an analog for this. We're not going to get into fluvial, but right, the Green River channels, they're beautiful places. I've got lots of data sets on them. I think, again, these analogs are of interest. So we've been in and out of Bonneville for many years. I just want to highlight some of these features that we've been taking a look at with Paul and Jack. But J.K. Gilbert, one of my heroes, right? In geomorph class, you can't get by without me, right? Espousing everything J.K. Gilbert does. But in J.K. Gilbert's books, there are all kinds of amazing images. And the question is, how did these form? Right? How did these form? And J.K. Gilbert has a good idea, has some really, I think, spot on observations of these areas. I'm not going to go into details because we got people here who can go into all the details, but you know, we could take a look at the shorelines that are around here. We have the rise and the fall of the Lake Bonneville. When you have a lake that's rising and falling, and there's no more lake here except for a small little bit left, right? It produces a beautiful analog for me to go study at Lake Superior, and to study other lakes around the world, because I can go anywhere here and take a look at them. And so we've been working together at these different sites. There's papers on some of these, but I'll show you some of the images. Stockton Bar is a place I love to go to. We shot some of our original images, and what we can see is these angle of repose as this bar was building out. And I'll take you to 2 locations right here at the end, and we're wondering what was happening. And I'll show you the one this way in a cross section as we go through. And the cross section going across, we can see there's a core in the middle that they originally built out. And then we have angle of repose on both sides building out at this location. And there's lots of gravel operations going through this. And then if we go straight downwards, we can see the, again, angle of repose. So about, 34 degrees moving out. And then something happened. And then you have another movement of sediment in these areas. And so we've got more profiles in these areas, but with the GPR method, we can see through into Stockton Bar and get some ideas. The first foray down here when we were down was into Brigham City. Didn't want to do it. And Brigham City is an active gravel pit. I haven't been up there for years. I don't know if it still is, but it was an amazing place to go to because we have this outcrop that you can see. And we said, well, we should be able to emulate that outcrop. If GPR is a tool that can emulate the outcrop, we should be able to find it. And this is one of the profiles that we see here. And we were, seeing down 30 plus meters at this site. And that, to me, what you're talking about is a fan force at delta that's coming out and building in these locations. And so this builds a beautiful analog for places like Peyto Delta in the Canadian Rockies and for a lot of active deltas post-glacial. And so you can do diagrams of the from the faces of the gravel pit, and from the GPR profiles, you can see the continually progradational nature of this deltaic system. Point of the mountain, just south of here, paragliders. It's changed a lot since this photo, but we've done some work in these areas, and the idea of how does this tie in, right? In the sense of we have the GPR profile that comes in, you can progradational nature, the offlapping sediments in this area, and how does that tie in to the tectonically shattered bedrock off here? Did it erode first and then build out? And we can now play along with sediment models and lake levels to see what's going on as you have an erosional slope eroded off and then built up as the sediment comes in there. Let's move down to a couple sites near snowplow, right? So going out, that's where we're right now, right down moving through the desert. And for me, it's always a fascination, having grown up in the Pacific Northwest and living in Wisconsin with lots and lots of trees. You go to a place, right, there's no trees. You can see everything, right? And so going out there, and I take students on some of these projects, so the orientation, right, making sure you orient students what's going on and what's happening in these locations. So we're gonna get back up here. All right, so 2 items of interest is this V-bar coming right into here, and then snowplow situated down here. And in the project that Apologetic we're doing, they got some nice LiDAR imagery, very detailed LiDAR imagery. You can actually see the roads coming off and on. The question here is, what's the internal stratigraphy? How did these V-bars form? And I have been looking for years and years and years for V-bars on lakes and marine coastlines around the world. And you just don't find it, right? The closest thing is a cuspate, maybe a cuspate foreland, maybe, right? As we take a look at this. So we shot multiple ground penetrating radar profiles, as we talked about earlier. And from those, I'll show you a couple. We will do the 2 long ones to get an idea of what's going on here. And then the cross one right here. And so this is the upper one and the lower one. They're essentially horizontal, sub-horizontal reflections. They're aggradational. There is a slight dip that's going towards the end of the V-bar. And then when we take a look at that cross one, so that cross one will be right up near the end here. You see this feature right here, and then some off sloping here. We were expecting to see a lot steeper dips off the ends here that we don't see at this site, but there is a core at the center of this feature at the end. So is there something out there that's holding on? Is there some, we need to go back and do some more work. Take a look at those. So that's the V-bar. The question, it's always been, how did they form? We need to get some details on that. Then there's the snowplow, which I had never been to before joining the project. And this idea, right, that the snowplow built as the lake was rising. Okay. If you look at most textbooks that are out there, it'll tell you that you can't build landforms as lake levels are rising, or as we have right now with 95% of the US marine coastlines eroding, right? As sea levels are rising, you erode the coastlines. Well, if you look at the Curry diagram, that is not true. Because if you have enough sediment supply, you will build these coastlines out. So what we take a look at this area is we had to show that these coastlines were built out as lake level was rising here. And so this is one of the LiDAR imageries there. They're beautiful. As we go out, and we can go from the lower one down here, and then we get higher and higher as the lake level gets higher and higher. And so what we decided to do is to collect some GPR profiles here to see what we could see inside these. And we'll take a look at one that we ran just straight along, because this should show, like as we talked about earlier, horizontal reflections. And we get a velocity here about 0.1. So mostly sands that we take a look at. And again, this is horizontal to subhorizontal, same as that one of those wings on the V-bar. At that site is what we're taking a look at before our signal gets attenuated. We then take a look at a site that is coming, if the waves are coming in at this angle, we should see that dipping out at this site. And this is what we see. We see about 4 to 5 degrees at about, 4 to 5 meters in depth at this site. Going across the whole profile, what we've seen is that there's usually a core in the middle, and they're building out in both directions here. We ran a long profile across this site, and what you can see is off both sides, we have the dipping nature about 4 or 5 meters thick, so that I think that's wave-based, storm wave-based that we're seeing, that's built up in both those directions. And then in the middle, we have another core that essentially builds up aggradationally, and then you have your sediment coming off both sides. We moved up one more, up to the top, and one of the ideas here is that we should see the same thing. So going with longshore drift, horizontal to subhorizontal reflections, and then going towards where the waves are going to come in here. And we can see that dip going down to about 3.5, 4 meters, probably about 4 to 5 degree dip. So one of the questions are, if this is true, if this is onlapping, if this is true, it should be onlapping the bedrock on that side, or alluvial fans if they were in that area. And so what we did is we shot up the side. And what we can see as we shoot up the side here with everyone, we can see there is the bedrock coming down here. And then we can see the longshore drift or a coastal process is onlapping the bedrock in this area and saying that this was built onto that bedrock. So if it works here, it should work in all the basins, all the pluvial systems. This is one from Death Valley at Beatty Junction, the barrier bar system. This was a class project, and the class was out collecting data, doing all kinds of the projects we're talking about. And what we can see here is this horizontal to subhorizontal, and then we see this erosional truncation and these dipping 3 to 4 meter thick, basically a coastal foreshores building out over time. Aeolian environments. Let's hit on a couple here. This is from Cape Hatteras out in North Carolina, where we have one dune with soil, 2 dunes nicely migrating along, and then a 3rd dune migrating package on top of it. And this is, we've dated these. You can take a look at the packages going in these areas. We've also worked in places like New Zealand, Farewell Spit. And if we go out to the end, it's a very, very wind-blown environment. And you get these big dunes that are migrating across during low tide. During high tide, they're completely covered. But if you shoot on these, you realize how windy it is. But as we collect the data, we can see the angular repos that are building these dunes as they're migrating. And these dunes basically migrate right into the ocean and disappear. And so it's pretty neat to see the building over time. The dune up on Lake Superior. And what we can see is once we have these details, we can collect a lot of detailed interpretations. We've got dates on these. And earlier, people didn't think that was an active area. There were basically in the northern part of Michigan, there was no vegetation, and dunes dominated the landscape in these areas. And we can go to Aeolian in Zion National Park. I saw this site on my honeymoon. I had to stop. I had to get out to the site. And I've gone back a couple of times. When you drive around the corner, you see this. You see multiple packages of Aeolian dunes migrating through this area. And I'm saying, can we see this with the GPR? Can we see those details? And the answer is yes. We could pick up those packages and take a look at the details. We can take a look at the bounding surfaces. And then I said, okay, this is a lower resolution. How high of a resolution can we see? And this is 900 megahertz data. And I believe these are the bed sets of one dune package. And so we can start picking those up and seeing how detailed they are. 3D cube. It's a lot that could be done with this. I've had a couple students take a look at it, but picking up the details within there, seeing the changes within there. Some of the bed sets will die out within there, which is expected, but there's more we could do there within Zion. I'm just going to finish up talking about using everything that we just talked about and trying to put it in perspective of a population of 6 million Jews, as well as more marginalized people being killed at these sites, and seeing how we can help out. And we can see this ties on to recent events, dying within Ukraine. I'm in communications with people there of going back once the war's over. Can we locate these sites? We've had very much a good different documentaries documenting some of the research we did. We just had BBC release one as we go through. But the big thing that I'm interested in educating is in Wisconsin, there's a 482% increase in anti-Semitic incidences all across the state, not just at universities, all across the state. This is the graduating class of one of the schools in Wisconsin. This went worldwide, right? There is no education at a lot of schools about these issues, right? So I'll just show one site that we work at in Lithuania, Vilnius. I had to look up where Vilnius was when I first was invited to join. But these are students the first time, right? They get a passport, first time they left Wisconsin, first time they, basically travel internationally, first time they've been on a plane. So these are a lot of firsts for a lot of students as they go. In Vilnius, there were hundreds of synagogues. This is the only synagogue left post World War II. This is where you could say we'll be there in a couple months, 2023. This is still the neighborhood where the Jews lived, right? Because Vilnius does not know what to do. What do you do with a neighborhood when their population have been killed? And so this is a huge problem at these sites. This is, Starbucks is off on the left here. And this, you're looking down here, was the old ghetto gate. And so they document this. Up on the walls, you can see this documentation of where the ghettos were. And so we were asked to try to find this great synagogue and Schulhof of Vilna. And this is the synagogue itself to the left. You'll notice that it is just below the steeples of any other religious structure, because by law they have to do that. They can't be higher. And so what they did is they built a floor down to be able to still have the massive structure in these sites. And why is this famous? This is the rabbi who brought, you could say, Judaism and modernized Judaism, you could say. That's the way it's explained to me as it goes through. And so you have all kinds of visitors, all kinds of people from around the world visiting this site. And this great synagogue was plundered, damaged in 41, demolished by the Soviets in 57. And then there was a school built on top of it. And so when we arrived in this kind of situation where there's the school and the kids are playing elementary school. And, we have to work around their schedule as it's going through, which is understandable. But the idea is that underneath the structure lies the synagogue. And we can get the maps, and we can see number one, here's the synagogue. And then we have the school structure. And then you can see how it was built in the bottom here. And when we take a look at that, we said the Soviets probably collapsed the synagogue into the basement of the structure and then put the dirt on top and built the school. And so we collected data, we collected multiple grids. And Nova came out and did a project on this. And so you can go take a look at the details if you're more interested. Good. And we'll go forward. Oh no. So we'll go past that one. So when we collect profiles there with the students, I'm going to hide some of these. We'll get profiles like this. These are time slices looking down into the ground. And if we highlight this, what you can see is that these structures, these linear structures, which are not the glacial fluvial outwash we would expect in this environment. And so we would pass that along to the archaeologists, along with all the grids that we've collected with highlights where we think you should dig. And they've been digging for the past several years. And we found the synagogue, we found the bema. The bema is the place where you would read the Torah and you'd find all these structures. And the mayor of Vilnius said, I am moving the elementary school to another location. All the kids are moved, and this now belongs to the Jewish community. That's happened in the last year. The Jewish community is taking the building down and then is looking at building some structure of remembrance at that site. But what happened to all the Jews that were in that area? Most of them were sent out to Ponar. Ponar was like a nice place to go for a picnic on a Sunday afternoon. But the Soviets had built a large holes in the ground for fuel storage. And when the Nazis took over this region, right, they said, this was a good place, right, to kill these people. And the reason we know this is someone documented everything that was going on, going in and out there, and then buried, because they were scared they were going to get killed, and they buried their documentation in the garden. And that has been used. So when you go to Ponar, we see multiple large pits. And this is the example of a pit and the Soviets memorializing the ones who died in the war. And it's a tough thing to bring students to, right? These are issues that are well beyond, you could say, the textbook. Now we're on the ground. We're working on top of potentially 70 to 100,000 bodies that are below your ground at these sites. And so we use all the information we can. We use German photos, the Luftwaffe. We can locate certain features within there. We can use LiDAR and we can see the depth here of the pits. There's a depression here that we're interested in. And we can see those depths within the forests and some of the lines. Why is this of interest? You can see the railways. Lithuania became independent in 91 and has joined the EU, and they're expanding greatly. And so they don't want their railways to go through any mass burial sites as they're going through that area. So we use electrical resistivity tomography, and you can see from the electrical resistivity tomography colleagues have done, you can see a pit within here. This sediment is glacial fluvial outwash, much different than a pit full of buried bodies in this kind of area. And so they did a star pattern on top of there to try to locate the grid. And from that star pattern, we went in with ground penetrating radar. If we highlight this area, right, what we can see here is there is horizontal to subhorizontal reflections, which would be that glacial fluvial outwash that we would expect. And then we have truncated layers within here. And as those layers get truncated from here to here, we now move into a hummocky reflections within these areas. And this is essentially the bodies that have been buried, but it gets one step worse, is that when the Nazis were losing the war, they realized they better hide the evidence. And so they dug up all the bodies, used all the trees in the forest, burned all the bodies, and then reburied those materials. So that's why this pit was never found, because it was all filled in all the way up to the surface that they had to take a look at. And so using that GPR, we take a look at, you can see that oval feature, and that would be that pit. We give this to the archaeologists, and they basically put up a memorial. There is no excavations due to Jewish burial laws. These people have been traumatized once. We're not going to re-excavate the bodies. And so this is the same kind of way that I would work with native groups in North America, of trying to find the sites and then pass it off to the elders of the tribe and to try to locate those areas. There'll be a film coming out later this year on some of this project. Just to finish off, right, we have all these great models that are in our textbooks, and they're great models, and they're based off a lot of the work that we do. But they're constantly, right, that's part of our job, is to constantly refine them and to take a look at them. I mentioned earlier, this idea of washover, I think is there somewhere, but it's not as dominant as we think it is. It's just one example of the others. We also have these huge tanks. This is at St. Anthony Falls Laboratory that we can use to try to emulate these features that are out there. And they have wonderful locations there. I've got lots of data sets if anyone wants to play around with. I'm at an undergrad institute, so I always have extra data sets that I can get finished. But just to finish off, right, I think you must learn to read the record. You need to know the environment. You need to practice to get good. It's not a quick thing to get up and running. And sometimes GPR doesn't work, and you need to know that, and you need to be able to say that as you go through. Thank you very much.